So continuing on with our hypothesis testing of the mean, we just went through an example of testing the density of sandstone from a sample against a known population. And we found that the z-value we got was greater than the critical z-value given our significance level. And that caused us to reject our null hypothesis, which was that the two populations the sampled population was the same of the known population. And because we formulated our null hypothesis like that, then we can evaluate the probability of being wrong, of making a type 1 error, which was equal to our significance level. Now let's look at a second example. So let's imagine we make another sampling of a different sandstone. And in this case, we get a mean density of 2.29 grams per cubic centimeter. And again, we have a lot of samples, so n is equal to 5, so we can still use our normal distribution. Or we can still assume that this the sample mean will follow a normal distribution. So with that new value of x bar and the same parameters of our test population, we calculate a new z value of minus 1.17, and again we have alpha is equal to 9.5%. So the critical z value is still the same, 1.67. And we find that this new z value is the absolute value of that new z level is less than our critical value. And so because we got this result, then the sample that we've made is more likely, it's within the, what is that, 90.5 confidence interval of the mean of the test population. So we cannot reject H0. And we can't reject it to the specified significance level, 9.5 significance. Okay, so what do we do now? So we're tempted to accept H0. And if we accept H0, we would reject H1. But if we did, and we turn out to be wrong, we would have made a type 2 error. Okay, so what is the probability, if we were to accept H0, what is the probability of making a type 2 error? And if you need to stop the video and think about it, I encourage you to do so. So that's the question. What's the probability of making a type 2 error? That is, that we accept H0 and say that the sampled population has the same mean as the previously studied population. If we conclude that way, but we're actually wrong, in fact, that the sampled population comes from another population. What's the chance of that? Well, the answer is we can't tell, okay? The main reason is we don't know what other population distribution okay, it might come from, and we don't know what other population distribution to test to evaluate our chances of making a type 2 error, right? So remember when we in the first case, when we were tempted to reject H0, okay, because of our high Z value, we had a known population distribution to evaluate our chances of being wrong, okay? But in this case, when our Z value is lower than the critical value, we have no other information about the possible other populations that we could have actually sampled. And the fact that we cannot assess the probability of a type 2 error means that we should avoid at all costs making this type 2 error. And the only way to do that is to not accept H0. So we shouldn't accept H0. We should reserve judgment. Okay, so we don't accept H0. We reserve judgment. So we've formulated H0. Again, it was designed so that if it's rejected, okay, that we would be able to evaluate the probability of making a type 1 error. Okay, or in other words put, we really can only tell what something is not, okay, by saying what something is not. We have an information about a probability distribution, a previously studied probability distribution. Since we know that information, we can tell whether it's not from that, but we cannot tell what something is. Right? And the main reason is that is can have infinite possibilities. It can be anything. We don't know what it is. Okay, so through this example, I'm hoping you have a good understanding of how to formulate a null hypothesis and therefore an alternative hypothesis to test whether a sampled population, a sample, comes from a population that's that has the same mean as a previously studied population. Let's now consider a different situation, and this is section 2.2.1, and this situation involves testing for difference between population means of two samples. So say we take two samples and we want to know whether they come from the same population. Okay, so we have two samples and we make we determine the mean from sample 1, our first sample, and we determine the mean from our second So the question is whether the population mean that we sampled in our first sample is equal to the population mean from our second sample. Okay, so that's the question we're after. And so we need to formulate our hypotheses. So the null hypothesis in this example will be that mu1 is equal to mu2. And then likewise, the alternative hypothesis is that the two populations sampled have different means. Okay, so if the two populations that have been sampled indeed do have different means and the populations are independent of each other, then the difference in the sampled means, or I should say the difference, right, the differences in sample means will have its own distribution. So let's say delta x bar is equal to x1 minus x2 bar. Theoretically, that will follow a t-distribution. In other words, if we were to make repeated samples from the same two populations, and if those populations were indeed different, then the difference in the sample means will follow a t-distribution, and it will have a standard deviation of, let's call this sigma e. This is the standard deviation of the difference in sample means, and that's equal to sigma sub p times the square root of 1 over the size of the first sample plus 1 over the second sample. And sigma p is the pooled standard deviation, and that's defined as the square root of n1 minus 1 times sigma 1, the standard deviation from the first population, the squared standard deviation is the same as the variance, plus n2 minus 1 times the variance of the second population within the second population, and that's all over n1 plus n2 minus 2. And I want to make this clear that the square root applies to the whole thing. So, okay, so that's, the whole thing is under the square root. The degrees of freedom are, the pooled degrees of freedom are the total number of observations minus 2. Okay, and the statistic we have to calculate is t, and that's equal to x bar 1 minus x bar 2 divided by sigma e. Okay, right. That's our t statistic that we are going to calculate and test. So following the normal steps, after we measure our population means, we have to define alpha, and that's the significance of our test again. And then we would find the critical value of t. And our critical value is the t value for the specified significance. and the number of degrees of freedom. And then if our measured t value is, or the absolute value of t is less than or equal to t, our critical value of t, then what do we do? What does this mean? Why don't you go ahead and think about what we would do. Would we reject or accept our null hypothesis? And the answer is we would never really want to accept our null hypothesis, but we cannot reject H0 if that's what we find. But if t is greater than our critical value, then we can reject H0. To the alpha significance. Okay, so if t is within the probable range, okay, the 1 minus alpha confidence interval, then the difference in our sample means is too small to say that the population, to say that we can reject H0, that the populations were equal. If the difference is large enough, then we can say that we can reject H0. In other words, that the populations are not equal to each other, and we could also accept the alternative hypothesis that they're different. And I encourage you to look at example 2-3 that Wessel lays out to illustrate this procedure in practice with some real numbers.